and such, right? And then this is a little white dwarf. Notice it's got a little blousy atmosphere. This is an artist rendition, right? And then this is the singularity. Notice it's got a little accretion disk around it, right? So there's stuff spiraling around the black hole. If there's material falling from space into this thing, striking that accretion disk, that could be a quasar. Quasars are just crazy, crazy bright. They could actually turn 10% of the infalling mass directly into energy. I mean, imagine this. Can you imagine this? 10% of the mass falling in turns into radiant energy. Right? So quasars are just insanely bright objects. This is a core of a galaxy. Oh, look at that. Looks like a black hole to me, right? Okay. So 10% is converted to energy, right? These are intense radio sources. When we look at the radiation coming from it, it's red shifted. Well, that's because the red shift is because if you think about this gravity well, right? This is like potential energy here, right? Or the sheet of rubber with the heavy object on it, right? The radiation, here's the black hole infinitely far down there or something like that, right? Okay. Here's the accretion disk. The radiation has to climb out of there. As it climbs out, its energy is E equals HF, right? As it loses energy, doesn't the frequency go down? Yeah, so as it climbs out of this potential well, it's losing energy, and the frequency goes down. The wavelength gets bigger. It's red shifted, right? And this is called a gravitational redshift. We'll calculate this. Quasars are usually in the centers of galaxies. Here's a very bright quasar. And this is something that's sort of interesting, is that quasars nowadays aren't very bright. There aren't so many bright ones. But when the universe was younger, there were a lot of very bright quasars. And so this implies that quasars fairly rapidly eat up all the stuff there is to eat, and then they're like a teenager looking around the house for food, right? Like, nothing to eat. Dang it. Nothing to eat in this house.
And so they tell the difference between a quasar and a star by how much stuff?
I think by the type of radiation spectroscopists can tell, right? You know, there's a difference. I wish I could tell you more than this. Accretion disks, they're ravenous. We already said this. They make tremendous magnetic fields, and then this is kind of crazy. They believe that there are jets on quasars. And they think that there's like little tornadoes on these accretion disks that are actually shooting stuff, kind of like the Wizard of Oz off into space. Yeah. Yeah, everything, right? Because it's spinning too fast, right? If our sun becomes a black hole, it'll just get dark here and we'll just keep orbiting it. In other words, if some deity came and just collapsed the sun into a black hole, we would not just go spiraling into it, right? Because at our distance, gravity would be exactly the same, right? We'd still be at some distance from the sun would still have its mass, the Earth would have its mass, the force would stay the same.
Then you think gravity would be
right?
less because the distance would be smaller, wouldn't it, by a little bit?
No, because it's center to center distance, right? So, right? So the galaxy's not going to just, it's not going to hoover up an entire galaxy because the galaxy's spinning fast enough for it to. No, because black holes don't become black holes by getting more massive, right? They don't gain mass; they just get smaller. Yeah, I mean the only way a black hole gains mass is that it does actually eat something, right? And it's like, oh, All right, hey, that's enough of this stuff. Let's take a look at. I made a link for here. If you go to here, this is the flow chart. And I want you to click on start and answer yes, no, and look at your little sheet. This sheet goes along with it. I want you to go through and look at all the little pictures and write down, just jot down a little thing for all the questions. You don't need to write a dissertation on it. Okay, let me show you something else. Okay, if you go to links, let's see if I put it on here.
Before we get to the flow chart, you just had a link. No.
Yeah, did I put the other link? I didn't put the link there. I'll put a link on the front page. Let me show you what I'm looking at. If you go to Google, and I've been finding this stellar activity. It's the first hit. Okay, the Chandra. This is an X-ray telescope. If you click on this thing, it loads up this. And it's a cute little interactive flash website. Um, from Harvard, yes. Chandra at Harvard. And it's kind of cool because it's like, ooh, look at the introduction, right? It's like, ooh. Milky Way contains several hundred billion stars of various ages, sizes, masses. Star forms when a dense cloud of gas collapses until nuclear reactions begin deep in the interior cloud and provide enough energy to halt the collapse, right? Okay, that's a cool way to say it, right? By far the most important factor is the initial mass of the star. This interactive piece illustrates a general way how stars of different masses evolve, and what the final remnant will be a white dwarf, neutron star, or black hole. Stellar evolution gets more complicated when the star is a nearby companion. For example, excessive mass transfer from a companion star to a white dwarf may cause the white dwarf to explode in a type 1a supernova. So, yeah, we're going to talk about that in a little bit here. The following tableau, so let's just go here. I'll show you what you can do with this. Okay. Now, if you take, you gotta click this. I just gave you guys a little star chart, and I had Natalie, one of my assistants, go in and just find a bunch of stuff like this. And they all start as a protostar. So the first step is protostar, protostar, protostar. I mean, they get smaller and smaller, right? Okay. This guy, if it's a blue supergiant, and they think it's about, the best estimate is 150 times the mass of the sun. If it's that big, right? If it's that big, then what happens to it is that it becomes something like Eta Carina, right? Its pair instability, thermal energy at that temperature has enough energy, right? Every particle has enough energy, enough kinetic energy to create positrons and electrons, right? These cause a massive explosion. This rips apart the star. So that is the upper limit, is about 150 solar masses. Beyond that, your pair instability, I just turned off the lights. These poor guys are taking the test. Okay. The pair instability creates enough energy that it's like a nuclear reaction that tears the star apart, right? And then if you look at this, less than 150 stellar masses, a blue supergiant star will collapse directly into a black hole. There's no red giant, there's no anything like that. It just cools down a little bit and then just boom, it's gone. Yeah? Right? And these guys just last, a million years maybe, right? Okay? If it's a bit smaller, then at least it has the dignity to do a type 2 supernova. And this is just the supernova of a giant star, right? So these blue supergiants have distinct trajectories, okay? A type 2 supernova, and then this is a black hole, right? Now we're getting down there, right? A blue supergiant, if it's only 30 times the mass of the sun, right? Only 30, right? Okay, then it will red giant, right? Okay, but it never does like a white dwarf. It just does a supernova, right? Red giant, supernova, neutron star, right? And it just depends on the size of it, whether it actually becomes a black hole.
This is Wolf rare.
Yeah. So at this point, right, it goes here, red giant, and then it can become a blue giant star like this, right? Okay, not a super blue giant, but just a blue giant, right? And so Wolf-Rayet stars are actually the cores of red giants, right? So when it becomes a red giant, it's such a violent thing that it blows off the entire mantle of hydrogen, right? And you see that core. It's like, ooh, look at that, right? Not for long, but there it is, right? Crazy, huh? Type 2 supernova, right? And now we're down to our sun, and this is the whole scenario we talked about, right? Sun-like star does the whole gamut, right? Red giant, it can become a planetary nebula like this, white dwarf, and then that's it. It's just going to peter out, become a black dwarf, right? Okay. And then red dwarf stars are just, that's all they do. Red dwarf, yeah. You still a red dwarf? Yeah. Still a red dwarf? Yeah. Right? They puff up a little bit just before they become a white dwarf, but they never really fully do a red giant stage, right? Then they're a white dwarf. And then, I love these guys, the brown dwarfs. Brown dwarf just fades out, man. These guys actually, brown dwarf is a star that never ever sustains nuclear fusion at its core. And so any radiation they give off is just from the magnetic fields whipping up the atmosphere, making it hot, because they've got a ton of spin to them.